Good afternoon, ladies and gentlemen. My name is Allan Fogwill. I am the Chief Operating Officer for PTAC, Petroleum Technology Alliance Canada, and I'm very pleased to present a distinguished group of speakers today to talk about automation. Automation is a big issue these days, and making choices about that automation does take up a lot of time and also includes some risk. So we're going to be talking today about various technologies from a very macro level to a very micro level to talk about how automation at those different levels can be of benefit to your company, either in terms of enhancing production if you're a producer or reducing cost if you're any overall company. And we'll talk about those costs, those benefits, those challenges, those opportunities as we go along with our program. Dean is president of Kinitics Automation Limited, and he's going to be talking about the KVA 38, a spring-loaded electric valve actuator. And for the audience, I wanted you to think about these two different areas. One is what we've been talking about with Amit and had was the idea of managing or management automation. Here we're talking about engineered automation. So, Dean, where you go.
Thank you, Allan, for that excellent introduction. So today, as you alluded to, we're going to be looking at the control elements that effectively control the flow of gases and liquids through energy facilities, equipment, and infrastructure. And I'll be providing a guide to basically transitioning away from venting pneumatics. So there's quite a few reasons why the industry is moving away from methane venting equipment, specifically pneumatics in this case. Some of the drivers have to do with regulations across Western Canada. And we've been seeing as recently as 2024 changes in the regulatory environment. So back in March, Saskatchewan recently issued their directive PNG 036. It was followed in British Columbia by an update to BC Regulation 282. And these regulations have now put in, let's say, mandatory changes to how companies are permitted to operate venting pneumatics. This change, of course, is in addition to existing regulations that are in place in both Alberta, BC, and Saskatchewan, which prohibit the use of venting pneumatic equipment. So we're seeing, not just now a regulatory framework that prevents the installation of venting pneumatics for Greenfield facilities. We're now seeing requirements coming out of provinces that are starting to target the large installed base of venting pneumatics. Saskatchewan being, let's say, the out front leader in this space, instituting mandatory reductions either by unit or by volume, even within the 2025 calendar year, with an ultimate goal to reduce 100% by 2028. So this guide is meant to be for EPCs and packagers and producers who are planning new infrastructure projects such as new wells, etc., that want to maintain compliance, but obviously don't want to completely reinvent the wheel when it comes to existing designs that they have tried and tested. It's also relevant to companies that are looking to address their installed base of venting pneumatics. So to provide a little bit of a preamble or introduction to the issue, the source of venting pneumatics, or the source of methane emissions from these devices, When it comes to control valves, which is a large percentage of the source of these gases, it's the practice of using gas from the pipe, so to speak, sometimes referred to as fuel gas, natural gas, or methane, as the mode of gas that runs pneumatics. So pneumatic controllers, mechanical computers, you could think of them, basically use this gas to control the position of control valves, shown here kind of like schematically or as a cross section. And these controllers effectively utilize the gas, but they don't destroy or consume the gas. It is a pass-through system where ultimately, once the pressure is spent or used up, in addition to other kind of escape mechanisms that occur, you now have a source of venting, either continuously or intermittently, depending on how the system is set up. So some folks may not recognize what's on the left, but they may be familiar with process control diagrams, PNIDs, PFDs, where they see a suite of control valves on their facilities, which are, again, controlling the flow of liquids and gases. You'll see pneumatic controllers here. I've wiped out the tag, but you'll have identifying information in the bubble. But what you'll see is sources for these pneumatic controllers, sometimes using the acronyms such as FG for fuel gas, sometimes IG for instrument gas. These are the mode of gas that's used to control that valve, and then vent OS or vent outside is sort of that telltale indicator that you're running a pneumatic device at that facility. The control in this particular example, I/P, is where you've got current control, i.e. a 4 to 20 milliamp signal coming from your SCADA system or PLC system, driving the pneumatics, and that's effectively controlling, in a lot of respects, the flow of that methane gas out to atmosphere. Now, if we look at how to address this, either for greenfield projects where you may not want to reinvent the process, or for projects where you're looking to reduce your venting volumes. In a lot of cases, the valve itself is not the culprit, or is not necessarily the target for addressing these venting volumes. It's really the actuation system, the pneumatic actuator and associated controller that needs to be addressed. So there's a lot of benefit and value with reusing that valve. So really the attention turns to the actuator. What can we do to automate this control valve in a way that doesn't introduce venting pneumatics? So we're going to, through this guide, address different considerations such as operating environment, mechanical interfacing to the existing valve, how you're going to power and control it, as well as safety considerations. So in this guide, we're going to use the Kinitics KVA38 as an example replacement. So this is a zero-emission electric globe valve actuator that features a built-in return spring, suitable for new sites as well as brownfield retrofits. That's been designed to provide the lowest cost of ownership to the users, both from a combined consideration for CapEx, but as well operating costs. And at least in Alberta, through the tier system, it is eligible for generating carbon credits by offsetting gas released from a brownfield application, such as a low bleed venting pneumatic controller. So let's start at the valve. First step is looking at the valve travel and thrust requirements. Travel is usually the easiest thing to find. Pull up your valve spec, pull your valve list, and you can usually identify the type of valve it is and how much lift there is. Sometimes you might find a special case where the valve may be traveling, rated to travel 3/4 inch or 19 millimeters, but in your operation has been intentionally limited, let's say to 1/2 inch of travel. So you can then choose to acquire an actuator that can either do the full lift or just the rated lift that the application requires. The other component is thrust. So important to remember with globe valves, they work up and down as opposed to a rotary valve, which is turning or torquing. So you need to consider how much thrust you need in order to basically keep the pressure in the pipe, so to speak, when the valve is closed. So you need to look at the type of valve, whether it's balanced or unbalanced. In this case, we're showing an example of a D-body valve. So this is an unbalanced valve where the pressure is being held back by a plug that's seated into a valve seat. And when it's holding back pressure, with the pressure side shown on the left here, you have to develop at least enough thrust to overcome that unbalanced nature. So that does include, I'm going to skip to the third point here, the maximum differential pressure. Look to your process flow and P&ID, look to your design to understand what the possible maximum differential pressure across that valve is. You combine that with the port size, or otherwise known as orifice size, which is taken as the cross-section, at least in the unbalanced valve, of the plug. And try to remember that it's not the size of the valve that matters in this case, it's the size of the port. It's very easy to confuse this one. A 2-inch valve doesn't necessarily have a 2-inch port. These are very different things, easily confused. But by combining the port size, you get your cross-section area, I should say. You look at the maximum differential pressure, and now you can start to get a sense of how much force you need to hold that pressure back. And then another consideration is the sealing class, just how tight that needs to look. Again, we're not suggesting any change to the, let's say, tried and true process control. It's more of get the data you need in order to evaluate an actuator for replacing the venting pneumatics. Other considerations include the operating environment, a very important safety and jurisdictional regulation consideration is the hazardous area location. In Canada, we're now using the zone system. So look at your zone rating, could be zone 1 or zone 2. In the case of the Kinitics valve actuator, it's rated for class 1, zone 1, so it's applicable in either zone 1 or zone 2 configurations, as well as div 2 for the legacy sites. You can also look at the temperature range, especially the low temperature range for those who have some exposure experience to the weather. We just need to step outside today to kind of feel what that is like, and it can be rough on some equipment. In the case of the Kinitics KVA 38, it's rated down to -40 degrees Celsius, so it can handle the cold. Can't work in outdoor climates or outdoor installations. And it's good for up to 50 degrees Celsius. So covers a wide range of operating temperatures. And now we can look at, how do we mount it? So typically you'll be looking for a valve bracketry solution, which is intended to basically space the actuator apart from the valve, shown here on the right. You need to consider the coupling. This is sort of nuts and bolts considerations, but better to figure it out before you go to site and realize you've got the wrong, thread matching. A lot easier to figure that out. Obviously in Greenfield, when you can do it in a shop install, but if you have information on the valve, we can use that to identify the right hardware to allow you to couple the stem, mount to the bonnet of the valve, and otherwise then transfer the load from the actuator to the valve, i.e. that's the load of the internal spring, which can then do its job, keeping the pressure back in the valve. Now look at power systems. 120 VAC or 24 volt DC has a lot to do with your on-site infrastructure. The consumption or the power demand is always an interesting conversation. It really comes down to what your process looks like. So consider your process. Whether you're doing dump valves, so intermittent lifting and dropping can be very power efficient on a snap acting case, or if you're looking for constant modulation for back pressure control, for example, also a consideration as well. So bring some process information and we can help you with power demands. It is not a simple answer in any case. As far as control system interfacing, the example we're using today is an analog input. So we're going to use 4 to 20. Serial communication or discrete points are also available. And you can now maybe also start to explore some automation enhancements. Position feedback, something maybe not available before, to actually tell you where your valve is, as opposed to just commanding it and hoping for the best, as well as advanced diagnostics to tell you how the actuator is doing and potentially even the health of the connected valve, all providing you with intel that you might not have otherwise had with your old infrastructure designs. And lastly, fail-safe is a key consideration. If we go back to that image of the process control, FC here stands for fail closed. The number above it, 2. That's a 2-inch valve. Again, remembering that that's not a 2-inch port. So how to achieve fail closed? With the Kinitics valve actuator, it is a spring-loaded valve. So if you lose on-site power for whatever reason, if you lose a control signal, even when the actuator is in a cold, dead state, the internal spring will return it to the closed position. This is very much like how the pneumatic example at the start of the guide is operating, and this is how the KBA 38 works. If you're looking at alternatives such as motorized operated valves, you're going to have to consider other things such as the super cap or battery backup that is essential to providing an alternate form of power if it goes dark, that is site going dark or actuator going dark. Of course, none of these solutions can replace whether the motor fails, in which case you're dealing with a fail in place and it has to be picked up in your HAZOP studies. So ultimately, it's up to the designer how they're going to achieve fail-safe, keeping in mind the additional CapEx that might come with some of the battery or super cap backups, in addition to the additional control systems that require detection and smart switching to swap these systems in. Alternatively, you can stick with the fail closed feature of a spring and take some comfort in that sort of tried and true method. So at the end of this guide, let's take a look at where we ended up, and perhaps let's also see where we started. We have either a legacy or greenfield D-body valve with a pneumatic controller on top. Really, neither the valve nor the actuator is particularly relevant in this case, but here we're trying to maintain or reuse that valve, and we have now, by switching to an electric actuator, we've kept the valve in place, saving either engineering time or equipment cost. We've eliminated the source of methane venting, so we now have a zero bleed arrangement. And if you've set up additional, let's say, connections to the device, you've potentially now realized better automation through feedback and advanced diagnostics. So we present this solution and guide as a way for you to apply this to your separators, your artificial lift systems, pressure stations, blenders, metering skids. Really, it is applicable across the range for any automation system. And we welcome inquiries where we can help provide solutions. We have folks in Edmonton, Calgary, and Vancouver at the ready to help you with your problems. So with that, I'll hand it back to you, Allan.
Thanks very much, Dean. This is fascinating stuff.